Is it on?
That sounds definitely like, yeah.
Sounds good. Yeah, maybe while I'm just waiting for the couple minutes, I'll just mention a few things about these reviews. So, TASI reviews are great, and they're great TASI notes. If you look on the archive for something, if you put in or to Inspire's TASI lectures on something, you'll often find some great lecture notes about different topics, like TASI lecture notes on anomalies by Jeff Harvey, for example, and many other things. And now you could watch videos. So from TASI 19, there are videos, and Clay Cordova gave a course on kind of introducing supersymmetry and many of the methods of supersymmetry. So I won't really have time to go into that much detail. I'll be very sketchy at some places, but just try to highlight some of the physics and things. I have some lectures on supersymmetric gauge theories and renormalization group flows, which are sort of similar to these ones, although I basically started from scratch with these ones and tried to put in some newer things. And then there's some great lectures also by Yuji Tachikawa on anomalies. I have some old reviews with Maddie Seiberg from a long time ago, and then there's some more modern reviews by Yuji Tachikawa. The first one is on n=2 theories. The second one is on n=1 theories. And then there are these great lecture notes by David Tong on different topics, and especially the one on gauge theories will be relevant for here. Okay. Looks like it's right on time now, so maybe we'll just start. Okay, so I imagine quantum field theory as like some kind of mystery machine where we could put in some kind of input and see what the output is. And sometimes, let me get some chalk. Sometimes we call this machine the path integral. So we have output we write it as some kind of functional integral. And so we could put in some input and then see what the machine spits out as its output. And by choosing different kinds of inputs, we can learn a lot about the machine. Sometimes it gives us some surprises, and we try putting in all sorts of strange inputs and seeing what comes out just to play around and see how the machine works. And so here I'll be talking about some aspects of the machine. Actually, if I imagine the machine, I think about it as like some kind of box with a question mark on it, and then there's a dial. And the dial is the renormalization group scale. So I'll be talking about these renormalization group flows. But so we turn the dial and see what happens as a function of the renormalization group scale. And the machine is kind of mysterious because it's not always clear, given the input, what the output will be. So just to mention some examples. Oh, but actually before I mention the examples, also we know that sometimes this description isn't quite good enough because there are theories which are called non-Lagrangian theories, where we don't really know how to formulate them as the input, but we can still study them using other methods like constructions from string theory, like what that Quora talked about. Some of these examples of non-Lagrangian theories are higher dimensional theories like 5-dimensional interacting theories or 6-dimensional interacting theories. And for those theories, supersymmetry plays an essential role. And actually, it's amazing how much supersymmetry has sort of taught us about the machine. So even if we don't care necessarily about supersymmetry, we might be skeptical that it exists in the real world. It's useful for learning more about the machine. So just to give some kind of appetizers of what the machine can do, if we input 4D Yang-Mills theory, then we have some renormalization group flow with a question mark because we can't really follow it in general. And then the output could be a mass gap confinement. So this is an unsolved Clay Prize problem. Maybe someday one of you will solve the problem. But we have strong evidence that this is what happens, and we believe this is what happens. But the theory that we put in has massless field, only massless fields, like massless gauge fields. And the theory that the machine spits out has no massless fields, but instead just some gapped spectrum. Another thing that we can do with Yang-Mills theory is we can turn on a theta angle, where this theta angle couples in the input to the second Chern class of the gauge fields. And this thing looks trivial in perturbation theory. You have to, in order to see the second Chern class, the integral of the second Chern class of the gauge fields, this is called the instanton number. In order to, and it's associated with the pi3 winding of the gauge group G. In order to see that, you have to have this non-trivial winding configuration, which you'll never see in perturbation theory, but it could have some dramatic effect in the infrared. Like, for example, it might lead to some spontaneous symmetry breaking of its discrete symmetries. Another example is we can start off with 40 Yang-Mills. With some massless matter. In some representations of the gauge group. And depending on what these representations of the gauge, actually let's call the gauge group little g. Depending on what these representations of the gauge group are, we might have, for instance, spontaneous symmetry breaking of some global symmetry. Some subgroup. This is like what would happen in QCD if the quarks were actually massless. And then we have massless pions. We could have massive pions if we turn on mass terms here, or if we turned on other interactions. But if they're just massless matter here, we would have massless pions, which are Nambu-Goldstone bosons associated with the spontaneous symmetry breaking. And maybe let's also mention for fun that there could be Wess-Zimino-Witten terms. G is 't Hooft anomalies. For example, in real QCD, we have an 't Hooft anomaly. I'll be discussing more about these 't Hooft anomalies, so these are just some appetizers. We have an 't Hooft anomaly associated with SUNF left cubes, which is NC, and so there's some Wess-Zimino-Witten term with coefficient NC. Another thing that can happen is we can have 4D Yang-Mills. With massless matter and some other representation. And for example, here in the case of QCD, what I mean in some representations is that this is NF below some physical value. And here, what I mean when I say other representations is maybe the number of flavors is bigger than some other critical value, which may or may not be the same as that one. And then in that case, maybe I should keep putting question marks because we can't actually follow these RG flows. And then in that case, we can instead flow to a conformal field theory. So this is with interaction. So here in this case, the theory is infrared free. The theory in the deep infrared is free, whereas here we could have an infrared interacting theory. Let's see. Just to mention another example, I'll be discussing some things in various different space-time dimensions. When I was planning these lectures, I was trying to decide if I should just stick to 4D or talk about things in other dimensions. So I'll be some things in different space-time dimensions. So as another example, we could look at, yes? Oh, yeah, yeah. Yeah, good idea. Thank you. Thanks so much. Okay, another example would be we could start with some 2D quantum field theory. With scalars in some target space. So here I mean that we have a Lagrangian which contains where this is some metric for this associated space. This is what we would call a nonlinear sigma model. And we can study this nonlinear sigma model. It has various different possibilities. Like for instance, if the nonlinear sigma model is CP1, maybe I shouldn't draw it this way. Which is like an S2, then in this case, the output is gapped. So it has a mass gap, and it's actually an integrable of some solitons. With some exact S matrix. Okay, so that's one possibility. Another possibility is we can turn on a theta angle, which is equal to pi. And here the theta angle is associated with some pi 2 of the target space. So there's some winding with pi 2 of the target space. And if we do that, again, we don't see it in perturbation theory, but it leads to a totally different output. In this case, the output is the 2D scalar. Which lives on some circle. This is what you heard a lot about last week in Nadi's lectures and also in Yifan's lectures. And the radius here is radius where there's an SU2 symmetry, the self-dual radius. So this is a theory where, again, the input and the output look totally different. And we can't follow the flow in detail. And then just, there are these theories that I briefly mentioned where we don't know how to formulate them in the UV, but in the infrared they can flow to some 5D superconformal field theories, 6D. so maybe I should just ask if there's a questions. I haven't really explained any of this, but this is just to give some motivation.
So all these question marks, how much of a question mark do they imply? Like, do we know nothing? Do we know something?
Yeah, okay. Yeah, so the question was, how bad are the question marks? Can we say some things? And in some of the cases, we can, that's a good question. So for example, in 4D Yang-Mills, one thing we can do, which is what Tom de Grand does, is to put the theory on a lattice. And so we can just study the theory on the lattice, and we can actually see, by putting the theory on a computer and doing the lattice theory, that there is a mass gap in confinement. Also, I'll be discussing some variants of 4D Yang-Mills with supersymmetry where, again, there's a question mark, but you can go a little bit farther and see a bit how the mass gap in confinement can arise from, for instance, monopole condensation. Many of these things are motivated by symmetry arguments. And so, here, once we have spontaneous symmetry breaking, then the theory, at least in the far infrared, is largely dictated just by the symmetries. But we can't really follow it in detail. Here, in this case of Yang-Mills theories with massless matter and some representations, one thing we can do is we can go very close to the boundary of asymptotic freedom. And then we can see this conformal field theory phase in coupling. These are called Banks-X fixed points. And so that's something which, in principle, we could study in perturbation theory and really follow the RG flow. So for all of them, there's kind of many interconnected hints and checks. Basically, often what we do is we try to guess what the output is and then do many checks. Any other question? Okay. So I wanted to say some things in general, about quantum field theory in different space-time dimensions. And so if we have some sensible quantum field theory in d space-time dimensions, we could consider on different space-time geometries. And so if we wanted to, we could consider it on some d-dimensional space-time, which is maybe some d minus n dimensional space-time times some sigma n. And one thing that we can do, we can take this theory, this part of the geometry to be small. And if it's small, then we can just kind of look at the Fourier modes and throw out the high energy modes as we go towards the infrared. And basically what we're doing is like a compactification of the quantum field theory on this sigma n, and then we can get some low energy theory. So as we go towards the infrared, we'll get something which is like a quantum field theory in d minus n dimensions. So this is something that we can do, go from some higher dimensional theory down to some lower dimensional theory. And in general, what we find when we do this is that the infrared theory is generally more quantum. Like these quantum interactions become more important. I was going to say more interacting. But they might be interacting in the original description, but they actually might end up being weakly coupled in some dual description. That can happen.
Is this RG flow? I mean, you are saying IR and DU.
Yeah, I have in mind something which is kind of like RG flow, but it's similar to RG flow where we think about just the basically just reduced to the to the low energy states where we throw out the high momentum modes on this. So it's similar to RG flow. We might want to make a distinction between this and usual RG flow. Yeah. Okay, so that's something that we can do. Actually, I see here, I wanted to, this reminds me, I wanted to say some more things about RG flow. Okay, so the picture that I have of RG flow is that, well, like we went on this hike on the weekend. So it's kind of like, you could think about RG flow as like flows of streams of water down some mountain landscape. And so we can picture that there's some kind of mountain, there's some height function, and then the RG flow is like some streams that are flowing down, or they might be some paths on the mountain that are converging, and then we go down. And what this is supposed to illustrate is the idea of universality. So by universality, we can have different streams that can flow into the same thing here. So we might think of this height as, for instance, this is the UV, and then this is the RG flow to the infrared. And different UV theories can end up at the same infrared point. So we might have two different paths which lead to the same theory in the infrared, and that's the idea of universality. And this notion of universality tells us that in some sense, information is being lost as we're doing this RG flow. So there's information loss along the flow because we're doing some kind of averaging. Like in the path integral, we average out fluctuations above some energy scale, and then that averaging leads to some kind of information loss. And this gives the notion that something is going down as we're doing the RG flows. So there's some count of the numbers of degrees of freedom in some suitably defined sense is decreasing. And so this is some intuition. And this intuition also helps us to understand or to constrain some of these flows, because if we can find some kind of count of the number of degrees of freedom, then we can check that it should be decreasing in all of these different levels that I talked about. So we can check this. And there are various ways of trying to formulate this and make it precise. One precise statement in 2D is Zamolodchikov's C-theorem. And there are different descriptions that we can give of the C-theorem. So one is just a statement about the endpoints of the RG flow. So if we look at the UV endpoints of an RG flow, that should be bigger than the infrared limit of the RG flow. So in this case, this height function could be, for instance, C. So as we flow down, the C is decreasing, and so if we can calculate it in the UV and the IR, we can check if this is true. And so we can go and look at some of these examples, like for instance, in this example, for the nonlinear sigma model on CP1, we would say here, CUV is 2. And here, because the theory is gapped, we would say C infrared turns out to be 0. So that's fine. Or if we look at this example where the theta angle is pi, again, CUV is 2. And here, C in the infrared is 1. You know, a free scalar field has central charge C equals 1. So that also checks. A stronger version of the C theorem is that we can define some C function along the entire RG flow. So we have some coupling constants. of the theory, which are functions of mu. And we could think about this kind of mountain landscape as some landscape of these coupling constants. So here what I'm actually plotting are various different GIs on this space. And then we can check that this function is monotonically decreasing, or that's the statement. And in 2 dimensions, Zamolodchikov gave a way to write down what this C function is, and then we can check. An even stronger statement is that the beta functions for these coupling constants are gradients of that C function. And so that requires you to introduce a metric on this space, which is called the Zamolodchikov metric on that space of coupling constants. And then that metric should be some positive definite metric. That's something that ends up being the strongest version of the statement. Okay, so that's in 2 dimensions. In other dimensions, well, one thing that I'll hope to talk about is in 4D, there's the A theorem, where instead of C, we use A. And so maybe I should just say that the idea is that if we look at a conformal field theory should have the trace of the stress tensor being 0. So the trace of the stress tensor in a conformal field theory, I want to say, is 0. But the idea is to look at it on some space-time geometry. So on some non-trivial M4 geometry. And then what you find is that there can be a conformal anomaly, where even though it's 0 classically, it ends up being something non-zero. One of the conformal anomalies is called C. This C is related to the stress tensor's 2-point function. And so that's also what happens in 2 dimensions. And that ends up being the coefficient of the Weyl curvature squared of this M4. And this was the first guess that people might have had for a C theorem in 4 dimensions, because it's also C, but this one doesn't work. And then there's another term which is called the A anomaly, and that's the coefficient of the Euler density. The C anomaly in 2 dimensions can also be thought of as this coefficient of an Euler density. What I mean by this is that just to check something, the stress tensor has operator dimension 4. The stress energy tensor in D dimension should have dimension D. And these things both of these terms are like curvature squared. And this curvature ends up having dimension 2. And so this thing is kind of consistent with dimensional analysis. These coefficients are dimensionless. And so Cardy conjectured that A satisfies this inequality. And actually, the first application that Cardy thought of for that would be to try to constrain this bound here, because you could compute what this A is in the UV, and then you could compute what it is for these Goldstone bosons in the infrared, and then you can see if you violate it. And what he found was that you basically never violate it, because in order to violate that bound, you would have to go beyond the asymptotic freedom range for the UV theory. So it's not an interesting bound in that case. But in the context of supersymmetric theories, there were many much more non-trivial checks, and this thing was always found to be true. And then a nice argument was given by Komorgatsky and Schwimmer. Okay, so this is a check that we have on 4D RG flows. And often so in principle, like we could try to calculate it in these examples. And if the theory is asymptotically free, then in the ultraviolet, we would just have free fields, and we know how to calculate A for free fields. In this conformal field theory phase, often we don't know how to compute exactly A in the infrared, so it's hard to check. But this is one place where supersymmetry, for instance, gives us a great help, because, so this is something that I'll discuss more later on, is that SUSY, if we have a supersymmetric theory, it allows us to exactly compute A in any superconformal field theory via a 't Hooft anomalies. And maybe, so just to say something about 't Hooft anomalies, many of you already heard about them from a little bit last week in Nadi's lectures. And many of the other lecturers will also be discussing 't Hooft anomalies. The great thing about 't Hooft anomalies is that they're constant along RG flows. And so, we could think about them as being somehow represented in this mathematical art device of the one higher dimensional theory. And that theory is some topological theory which doesn't care about renormalization group scale. So 't Hooft anomalies invariant so they're constant along the RG flow. And that's extremely useful because, for example, when we're looking at these different RG flows, if there's some 't Hooft anomalies, and if we have in mind that these two theories, UV and UV prime, flow to the same theory in the infrared, if there are any 't Hooft anomalies, we could check that the 't Hooft anomalies of this theory have to match the 't Hooft anomalies of that theory. Because otherwise, there would be a problem because they would also have to be matched along the infrared theory.
To what extent do we know if the A of the supersymmetric version could be the same as the non-supersymmetric version?
Okay, yeah, so the question was, how do we know if the A of the supersymmetric version, how is it related to the A of the non-supersymmetric version? Yeah, so in general, a supersymmetric theory would just be some particular example of a quantum field theory. And so whether the theory is supersymmetric or not, there would be some A which we out in this way, for example. And if it's a supersymmetric theory, then it gets contributions from all the fields in this supersymmetric theory. We could ask about a supersymmetric versions of different theories, and in general, the supersymmetric version of a theory wouldn't have the same A as the non-supersymmetric one. Like for instance, here, if I wanted to look at a CP1 sigma model, I could look at a supersymmetric version of this CP1 sigma model. So the way that I would do that in practice is I would add some fermions to here. And so instead of having this C being 2, I would have to add some fermions, and in the end, I would see that, for example, if I took it to be n equals 2 supersymmetric, basically the minimal kind of free matter fields in a n equals 2 supersymmetric theory in 2 dimensions would have C equals 3. And so I would have to add some fermions, and so in this case, the CUV would actually be 6. And then if I decoupled those fermions, I could try to go back to this theory without the fermions. So yeah, in general, the supersymmetric theory has some extra stuff which will contribute to the A. Yeah, thank you.
So with
Good. Yes. Yes. That can definitely happen. Yeah. Yeah. So sometimes there are known examples of that, where you can see it in supersymmetric theories, where the infrared theory here might have some emergent symmetry, and so it might be bigger than the ultraviolet theory. And so then maybe that's not manifest in this description, but maybe it is manifest, for instance, in this description. And so, yeah, so then you would just be checking 't Hooft anomalies for kind of the subgroup of the symmetry that you see in both of the UV and UV prime. Yeah, that can definitely happen. Also, I mean, I should have said here as another thing is when we look at these RG flows, is that there could be different basins of attraction. So just like with the hiking, we hope that at the end of the hike, our path will go down to the right place to exit. But if we go over to the wrong side of the mountain ridge, we might end up somewhere far away. And so that can also happen in RG flows. So there might be some kind of mountain ridge or something, and then all of these flows might flow to some infrared theory, and then these ones might flow to some infrared prime theory. And yeah, that's like what happens, for instance, in this case, where turning on theta equals pi totally changes the infrared fixed point. And so that's like going on some other side of some ridge. Okay. Yeah, so I wanted to give some. Oh, good.
So in this mountain picture, how should I think of UV fixed points in this picture?
Yeah, good. So the idea so let's say that we have some lake, which is like the UV fixed point of the water, and then and then we have to add some relevant perturbation. So maybe some of the water gets kicked somehow, and then it starts to go along some stream, and then it might end up in some other lake, which is some infrared fixed point. So this is the UV, and this is the infrared, and this is the stream leading to there. And as you get to the infrared, it's there's some irrelevant perturbation that's going away. And so, yeah, so the fixed points are like some places where it's stable, but then if you add some perturbation, you can float to some other one. Yeah, thanks. Okay. Okay, so just to give some yeah, so I wanted to illustrate a little bit this thing that I was mentioning about quantum effects becoming more important as we lower in the infrared, as we lower the dimension. So here D is the space-time. Dimension. And so one example would be if we look, for instance, at quantum electrodynamics. With massless charged electric fields. So here, charge. Like the electron. So we know in 4 dimensions, we have the beta function as a function of the coupling constant. It's usually called E, but let's just call it G. And we know that the beta function, at least near weak coupling, and so that means that as we flow towards the infrared, the coupling constant is going to 0. And so this is a theory which is infrared free. In 4 space-time dimensions. Actually, if we had massless, as an aside, with plus magnetic objects, dynamical. This isn't something that we know how to describe in a Lagrangian description, but if they're both massless electric and magnetic dynamical fields, the theory can flow to a conformal field theory. And there are known examples where this happens in the supersymmetric context. Actually, the fact that you need to have both massless electric and magnetically charged objects to get something interacting, there's a nice symmetry-based argument for that, which is that this theory, if we only had massless electrically charged objects, would have a one-form global symmetry. And that one-form global symmetry is incompatible with an interacting conformal field theory. So to get an interacting conformal field theory, you have to break that one-form global symmetry. And so if you only had massless magnetically charged fields, you would have an electric one-form global symmetry. Basically, you have to break both of the one-form global symmetries that you would have of pure Maxwell theory. And the way that you can do that is by adding both of these objects, and then you can have an interacting conformal field theory. So that's something that can happen. But on the other hand, if we look in QED3, version of this theory, that flows just on its own without having to look at this exotic stuff to a conformal field theory, depending on NF. In various cases, it can flow to an interacting conformal field theory. So this is an example where, kind of to illustrate that as you go down in dimensions, things become more interacting and more quantum. Yes?
In the example of with the one-form symmetry ruling out the interacting CFT, is it important that the one-form symmetry is spontaneously broken? Because I can imagine it wouldn't be spontaneously broken, it may just trivialize the time.
So the question was if it matters if the one-form global symmetry is spontaneously broken or not. Yeah, I don't know if it matters. Yeah, but by the way, so this argument also about, yeah, I'm not sure if it matters if the one-form global symmetry is spontaneously broken or not. By the way, like an old question was if this can happen, where maybe as you go towards stronger coupling, there's some UV fixed point. So this is called asymptotic safety. Where there would be like some UV lake, and then you perturb it away from that. That's like a conformal field theory, and then you go towards this. And this kind of argument about the one-form symmetry also rules that out. Yeah, but yeah, I'm not sure if it matters if it's broken or not. Okay. Yeah, there are many results about supersymmetric versions of these theories also. So a lot of a lot of these things could be checked a bit more in those contexts. And I might mention some examples if, time permitting. So far, I haven't said anything about actually doing supersymmetry. So this is all still kind of extended motivation about RG flows. Okay, another thing that we can look at are Landau-Ginzburg theories. And so, Landau-Ginzburg theories, we can think about some kind of description where maybe there's some Z2 symmetry that's spontaneously broken, or that it's unbroken in this case. And so we could consider, for example, some potential, which is like the first potential that you study in quantum field theory class. And then if we added some negative mass squared term, then it could lead to this kind of symmetry breaking. And then if we tune it to 0, we can go to this critical point. And so here again, we can ask if there's what happens in the infrared. And for d equals 4, it's infrared free. It's just like in QED because there's a positive beta function. So lambda flows in the infrared to 0. And so that's what happens in the infrared. And in the UV, it's not complete. Just like the QED theories in the UV is not complete. There's a Landau pole in the ultraviolet. So in those cases where there's a Landau pole in the ultraviolet, by the way, the idea is that if we think of the theory as a function of energy scale, then it's like the mountain has some clouds here, and we don't know what's behind those clouds. And then, so we just study the theory at low energies. And so at low energies, it's infrared free. But as we go higher and higher up in energies, so in the infrared, lambda goes to 0. As we go towards the ultraviolet, lambda might go to infinity, but we shouldn't really take that seriously because that's something beyond these clouds. And there's some other theory there that could UV complete it. So, so this is what happens in 4 dimensions. And if we look in 3 dimensions, this is this same theory flows to the famous Wilson-Fisher fixed point. So in 3 dimensions, the same phi to the 4th theory flows to some interacting conformal field theory. So we can just call it phi to the 4th. The lambda doesn't really matter. It flows in the infrared. So again, maybe I should put a question mark to conformal field theory. Let's call this the Wilson-Fisher conformal field theory. And this is a conformal field theory that's been studied. One way to study it is with the epsilon expansion, where we take d to be 4 minus epsilon. And then this is something that you study in quantum field theory class for this theory when you do dimensional regularization. And so we know if epsilon is small, there can be a weakly coupled fixed point. And then the idea is to take epsilon to 1 to get to the Wilson-Fisher fixed point. Or a lot of recent progress was based on the bootstrap program, where this theory can be studied using the bootstrap constraints. So this is some kind of interacting theory. It describes, if we look at like this, it describes sort of any universality class where they're associated with some Z2 symmetry. So like magnets, that's some critical point. There's this conformal field theory. By the way, in these applications, basically, the 3 dimensions are the 3 dimensions of our space, and then time doesn't matter. And so you can just do, classical stat-mech problems by thinking in 3+1 space-time dimensions by thinking about it as just a 3-dimensional quantum field theory. And so that's why this Wilson-Fisher fixed point, in 3 space-time dimensions we can think of as actually arising in physical 3D magnets. It's also the critical point that if you look at these phases of like water, then there's this transition between gas and liquid, which just ends, and so it's like the end point of that phase separation line. Okay, we could also look at 2D theories. And this flows to the C equals a half Ising theory. And actually, once we go down to 2 dimensions, we can also consider higher powers. So we could look at, so this has CUV is 1. So the ultraviolet theory is just a scalar field, which has central charge 1, and then the infrared theory has C equals a half, so that's consistent with the C theorem. We could also look at other potentials like phi to the 6th, and that flows to the tricritical Ising theory. And more generally, we can consider V equals phi to the 2n, and this flows to the minimal models. I should just raise this. Okay, let's see. Yeah, so maybe I should stop for questions. Mm-hmm.
Is there a formula for what the Cn is for n?
Oh yeah, yeah. So let's see, what is it? It's 1 minus 6 over something times something plus 1. So okay, so that's Cm. Now we just have to check how is m related to n. So if m is 3, then that's the Ising case. So right, so that's like, what is it? So m is, I guess, n plus 1. Yeah. Uh-huh.
Is there a same picture when you consider supersymmetry that for different potentials you flow to the supersymmetric model?
Yes, thank you, yeah. So actually I wanted to talk about the supersymmetric version, so I'll definitely talk about that. Yeah, there are nice versions of these where we can flow to the, there are minimal models for supersymmetric theories, and so supersymmetric versions of these will flow to those supersymmetric minimal models. Yeah, thank you. Okay. Any other question?
If I do a dimension analysis for this potential in 2D, like, if I have a kinetic term at 2D, I will analyze that the scaling dimension for that phi will be 0.
Good. Yeah, so in fact, yeah, this is exactly what I was about to mention. So the question was about assigning scaling dimensions to the different fields and what's the scaling dimension of phi? Right, so if we look at a free scalar field, Okay, so if we want to do dimensional analysis, we'll say that because the action should be dimensionless, so the scaling dimension of the action is 0. And so then that tells us that the classical scaling dimension for the Lagrangian should be D. And so this is the operator dimension. And so then the operator dimension of phi is D minus 2 over 2. And actually in conformal field theories, these kinds of free field results are generally become inequalities. And so in an interacting conformal field theory, scalar operators have dimension of the operator has to be bigger than or equal to D minus 2 over 2. So once we know some free field results, we can get some general inequality for operator dimensions in any interacting conformal field theory. I'll say a little bit more about that soon when I talk about representations for conformal field theories. But yeah, if you set D to be 2, like for this two-dimensional field, then you get that the scaling dimension of phi is 0. And so that's related to why this thing can be relevant for all phi. And what scaling dimension 0 means is that the phi 2-point function doesn't have a power law, but it has a logarithm. And so it's, it ends up being like the Green's function for the Laplacian. And so the Green's function for the Laplacian in 2 dimensions is a logarithm. And what that tells you really is that, like in the conformal field theory, we don't think of phi itself as being like a good operator in the conformal field theory. So like in the C equals 1 free boson that was talked about last week, if we were to list the operators, we write down operators as like exponentials of that. And so we have this momentum and winding numbers. Those are like coefficients where phi appears in the exponent. And then you have well-defined operator dimensions. You could also, the problem is really like a zero mode of the field phi. So you could also take derivatives of phi. And then like if you look at a derivative of phi, that ends up being related to a current, which is like the current associated with shifting phi. And so that also played a role in last week's lectures. Mm-hmm.
What's wrong with V was phi to some odd power?
Good. Yeah, so the question was, why are there only even powers here? So if we had an odd power, then the potential wouldn't be bounded below. And we could still study the theory, like if we had some potential where it's not bounded below, like maybe a potential which looked like this or something. We could still try to study the theory here in perturbation theory. And so like in many in some quantum field theory books, they start off with like phi cubed scalar field theory. And it's fine to look at phi cubed scalar field theory and perturbation theory. But if you go beyond perturbation theory, you see that the theory isn't really well defined non-perturbatively because it's unbounded below. But you don't run into that problem unless you really study it non-perturbatively. Yeah, thanks. Okay. Let's see. Okay, what else? Yeah, so let's think about some RG flow where there's some UV theory that I don't care about, and then in the infrared we flow to a conformal field theory. And here, before we get to that fixed point, there are some irrelevant operators which go to 0 as we go towards the infrared. And this is an example of an accidental or emergent symmetry. So as we go towards the infrared, there's some operators that are going to 0. They violate that emergent symmetry. But then when they go to 0, we have an emergent bigger symmetry. Well, let's just say accidental. Which is the symmetry of a conformal field theory. And we can think about the conformal group as being related to SOD comma 2. And so in the UV, we have Poincare symmetry. It contains Poincare symmetry. Actually, in the old days of quantum field theory, they were very interested in extending Poincare symmetry. Studying different possible symmetries, and it was seen that many, global symmetries have charges that are scalar operators. But we could ask, could there be symmetries where there's some extra conserved charges that aren't scalar operators, but that transform in other ways under the Lorentz group? And this is something that was studied by Coleman and Mandula. And Coleman and Mandula gave like a no-go theorem with some assumptions. And then the assumptions are violated in various different cases. And so one case where the assumptions are violated is this case. So in this case, we extend Poincare symmetry to a bigger symmetry, which is this SOD comma 2. And basically, their assumptions were that you can have, one of their assumptions was that you have a theory with an S matrix. And so you can have sort of asymptotically separated states that are non-interacting. You throw them together and see what kind of S matrix you have when they come out. And if you think about 2-to-2 scattering, for instance, 2-to-2 scattering, you would write down these Mandelstam invariants, S, T, and U. And then they satisfy some condition that S plus T plus U is some sum of mass squareds. So there's basically two independent Mandelstam invariants, which are like related to the energy and the scattering angle. And then sort of the argument is that amplitudes are analytic in those quantities. And so if you were to constrain it in any way, then you would end up requiring a trivial S matrix. But this gets around that because if it's a conformal symmetry, the interaction is there at all energy scales. And so you can't really have this picture of like asymptotically free fields which scatter with some S matrix. And so it's just a different picture. And so this is kind of an example of a loophole to Coleman-Mandula. And if we think about this SOD comma 2 as like a matrix, so this is the D and this is the 2, then here in this matrix, these are the charges. So the charges are like generators of SOD comma 2. And the generators of SON are like, the orthogonal transformations you get by exponentiating something with antisymmetric generators. And so this should be like an antisymmetric matrix. And so here these charges are like the angular generalization of angular momentum and boost. So those are m mu nus. And here we have some charges which are momentum. And then there are some new ones, which are the special conformal ones called k mu. And here we have the dilatation generator. This is like an operator whose charge is the dimension of the operator, that delta. And so this is some antisymmetric matrix. So it has minus the same things. And when you form representations, what you do is you start with a primary operator on the bottom. And what primary means is that there's an action of raising and lowering, where p mu is like a raising operator, and k mu is like a lowering operator. And usually we think of p's as being Hermitian operators, but if you do radial quantization, so this description is nice in radial quantization, you can think of k's as like the dagger of p. So one of them is a raising operator and one of them is a lowering operator. And so the primary is the one that you can't lower anymore. If you apply k to it at the origin, then you get 0. And then you can generate more states with P. And so these more states, we would just say, so this is some operator. This would be P mu acting on the operator, which we could just think of as like the derivative of that operator. And so we get all of these different states. And this is a multiplet. And the nice thing about conformal field theory is that many of the correlation functions of these things are called the descendants. So these are those operators, and then this is the primary operator. And okay, and there are various unitarity bounds. And the unitarity bounds follow because using radial quantization, we can make a connection between operators and states. And so if we take an operator O, we can form an associated state, and then there's some inner product. And we require this thing to be bigger than or equal to 0. So this is a requirement. As long as our theory is unitary, there should be some inequality like this. This two-point function, this inner product is like related to the two-point function of the operator. So we could think about this also as like a correlation functions of an operator at one point and an operator at the other point. And using conformal symmetries, basically we can map those points to wherever we want, and the only thing that really matters is some overall normalization coefficient, which is this thing. And so that should be true, for instance, for the primaries, but should also be true for all of the descendants. And if this is ever actually 0, what that means is the operator should just be 0. So sometimes what happens is we'll compute that for some descendant operator, and we'll see that we just get 0. And then that tells us that that operator has to be 0, and those are called null operators. And so if this thing is ever 0, then we call it a null operator. And for example, this inequality happens, so this has to be bigger than or equal to 0, and delta, let's just say it's saturated. If and only if d squared on the operator is null, meaning that it has, so this could be a primary operator, this is the descendant, I apply two momentum generators, and it's null because it has 0 inner product with itself. And then unitarity tells us that if it's a null operator, it just has to be 0 as an operator statement. And this is like the equations of motion for a free scalar field. So that's why it agrees with what we got here if we just had a free scalar field. And actually that tells us that this operator has to be a free field. So it basically has to decouple from any correlation function. And so you get interesting things when maybe you get boring things if the inequality is saturated because it becomes like a free field. Uh-huh.
Can you, you said that the operator being null is like an operator statement, but like, could you make that more precise? Does it mean, I guess, the correlation functions are 0 for that guy?
Yeah. So the correlation. So the question is how. What do I mean when I say that this? Yeah. So basically, like it's 0 at separated points. Maybe so when I say this operator is 0 in any correlation function at separated points, we get 0. We might, if we were to actually try to compute it from correlation functions of O, we might find some delta function contact terms or something. But yeah, but basically, if we look at correlation functions of this operator with other operators at different points, we get 0. And then that would tell us, so that's the statement about this level 2 descendant, is that it's 0. And then that tells us that the primary operator has to be a free field. And so the primary operator can have some correlation functions, but they're basically just like free field correlation functions. Yeah. Uh-huh. Great, great. Yeah. So the question was other exceptions to the Coleman-Mandula theorem. That's like the perfect timing because I was just about to talk about supersymmetry, and so supersymmetry is like one very famous exception because so what happens in supersymmetry is that which was basically they kind of assumed that the operators were scalar operators, and so in supersymmetry, the loophole is that the operators could be fermionic operators. And so that's one loophole. Another loophole is all of this stuff that we've been hearing about in many of the lectures about higher form symmetries. So in higher form symmetries, we also have conserved quantities that are like forms, like in a p-form symmetry, p-form global symmetry, the conserved charges are p-forms. And so that's also kind of outside of the Coleman-Mandula argument. The difference there, the way that it's a loophole there is that those things don't act on the way that we usually think about operators. So so the way that we usually think about operators is operators at a point. Yeah, maybe I'll just say it in words. So usually here, like all of these operators are operators at some space-time point x mu. And so these are called zero-dimensional operators. And zero-dimensional just because they're at a space-time point. But now what we've learned in recent years is that we can also have operators that are extended along lines. So in this case, we would think of this operator as being at a point, but there could also be line operators, like Wilson line operators or 't Hooft line operators. And so that's also kind of outside of the original assumptions of the Coleman-Mandula theorem to have these kinds of line operators. And so the higher form symmetries that maybe I'll mention briefly in some of these lectures and you'll hear more about in other lectures in the school are acting on these kinds of extended objects. So a p-form global symmetry acts on a p-dimensional operator. So like if we have a line operator, for instance, that's extended along a one-dimensional curve, and so that can carry a charge under a one-form global symmetry.
Ken, you've got about 4 minutes.
Okay, thank you. Yeah, so I wanted to talk, so basically this was all kind of my brief introduction, and now I'm getting, in the last 4 minutes, to supersymmetry. And yeah, so we have this machine, and with supersymmetry, we have a supercharged version of the machine. So so what are the supercharges? Well, I thought as a warm-up, I would kind of remind you of some things that Nadi talked about last week with this two-level system, because we could try to illustrate it with the two-level system. With h equals 0. So this is what Nadi talked about. And basically where I'm going with this is I want to introduce a partition function. Well, maybe since I only have 3 minutes, maybe I should just say where I'm going with this. So the usual partition function that we compute is trace e to the minus beta h. And so I want to talk about a partition function. So if we think about the partition function this way, we know that we can get this from a path integral. With Euclidean time. Which we identify on a circle of periodicity beta. And now what I want to do is I want to add fermions. And with fermions, there are two choices. So this is anti-periodic, and this is periodic. And the anti-periodic is sometimes called Neveu-Schwarz boundary conditions. And this is my chance to mention Pierre Ramond. The periodic is called Ramond boundary conditions. And so if we compute this partition function from a path integral, this has anti-periodic boundary conditions. So let's just say that this is like anti-periodic boundary conditions. The thing that I'll talk about more next time is we could also look at trace minus 1 to the f, e to the minus beta h. And okay, so that's this case. And adding in this trace minus 1 to the f basically changes the boundary conditions for the fermions. And so if we put this thing in, now we have periodic boundary conditions. So this is interval. This interval is supposed to be the Euclidean time that we have. Okay, so I'll talk about that more in the lecture this afternoon. But basically, in this example, for instance, we'll see that this is 0 in some, well, maybe I'll not say it's 0, but basically, this thing is what's called the Witten index. Of supersymmetric, if the theory is supersymmetric. So I'll talk more about this Witten index in the next lecture. Okay, any questions? Ah, good, yes.
Is there a way to think of that as like a generalized BRST procedure?
Oh, okay. Yeah, so the question was, when we set to 0 the null states, is there a nice way to think about this using like the BRST formalism? Yeah, I'm not sure if that's helpful. Yeah, offhand, I'm not sure if that's helpful. Yeah, so I should say like this condition about setting the null descendants to 0 leads to some very interesting constraints on the representations that people basically have worked out. And I haven't seen, I'm not thinking of a reference where they actually use that, but it might give a streamlined argument. Yeah.
Well, let's thank Ken for his nice lecture. Go get some coffee and be back at 10:45.
So for this, how should I understand? Like, there are a lot of topological lines on the right side,